When we developed the postulates of quantum mechanics, we made sure that they apply to the most general circumstances. This means that they should also apply to very complex systems, and in particular systems made of many parts. This is what we develop in this chapter and on relatively general grounds. In the next chapter, we will then address a particularly important version of such complex systems, namely systems made out of fundamentally indistinguishable particles. With this, we can then, for instance, provide a qualitative picture of the periodic table of elements and discuss the foundational problem of black-body radiation. But what we do right now will not just serve as a preparation for that next chapter. To the contrary, what we will address here are some of the most important conceptual aspects of quantum mechanics. The plan for this chapter is as follows. After some introductory examples, we will define what we mean by composite systems and lay out how we can describe them. There we will also identify the key concept of entanglement, which is arguably the most important quantum effect overall, and we will further develop this throughout the remainder of this chapter. We then illustrate this in more detail for the simplest example, that of a system composed out of two two-level systems. To obtain a deeper understanding of entanglement, we then identify a very useful tool for this description, the so-called density matrix. This provides the foundation for the description of a wide range of systems, such as systems that interact with their environment. We then see how this density matrix can be used in practice, first just for a single two-level system, and then we return to the example of two such systems. And in this way, we obtain a deeper understanding of entanglement. So, first of all, a composite quantum system is simply a system made out of different parts, where each part is a genuine quantum system in itself. This could be, for instance, a system made out of several point particles, a system made out of several spins, or say a particle and its spin. In all these cases, we have a clear idea of what the quantum states and observables are for the individual parts. Now we want to construct the same for the complete system. The general answer is very simple, in particular when we do this for these given examples. For a system made out of many point particles, we have a wave function that depends on all positions of these particles. So this wave function takes into account all possible configurations of the system, and its absolute value squared is then the probability density to find this configuration in a joint measurement. We can also define momenta, and this involves the partial derivatives with respect to these coordinates. We actually anticipated this construction already in the preparatory steps for the hydrogen atom, when we started with a wave function for the electron and the proton in the nucleus. We then separated the relative motion and the center of mass motion to reduce this to an effective problem of individual particles of the type we have studied till now. Analogously, when we have several spins, we have a vector of entries indexed by all combinations of these spins. And the absolute value squared gives us the probability to find this configuration in an experiment. Here we can also define all observables in a natural way, but I come back to this a little bit later as a detailed worked example. For the point particle with spin, we again have a quantum state that combines all possible configurations of the system. That's to say, we can find the particle somewhere in space with a spin, say, up or down, and the probabilities are the absolute value squared of the corresponding amplitudes. These we can then interpret as spatially dependent components of a two-component vector, or equivalently you can think of this as a two-component vector that depends on position. Here, momenta are still partial derivatives, and the spin observables are still 2x2 matrices. All other aspects of the quantum description are also very natural. For instance, normalization is just the sum of all of these probabilities. And we can also define, say, a probability for the spin to point upwards, irrespective of the position of the particle, which would be this integral here. And the dynamics is still prescribed by a Hamiltonian that is just made out of these observables. Even though this can now also involve combinations of observables from different parts, and this then represents so-called interactions. When we look at these examples, we see that the key step is to define the quantum state. And the common pattern is that this just takes all possible combinations of the states of the individual parts into account, where we apply this irrespective of the nature of the degrees of freedom. Before we formulate this in general, let me briefly mention a hidden assumption in there, namely that we can give labels to the particles 1, 2, 3 and so forth, which implies that we somehow can distinguish them. In the next chapter we will see how additional constraints arise if this is not the case. But even then, this will just be additional constraints placed on top of the general construction of the present chapter. So these examples serve as a useful guide to develop a general procedure to compose quantum systems into larger ones. And it will be enough to achieve this for 2 parts, as when we have a way to deal with this, we can iterate this procedure. This is what we will set out next. And as this will be temporarily a little bit more abstract, let me already state what we aim to establish, and these are 3 key things. Firstly, we demonstrate that everything remains well defined, and in particular that observables for each part of the system nicely carry over to the whole system. Secondly, we consider the nature of the correlations between the different parts, which leads us to introduce the notion of entanglement. And thirdly, we prepare ourselves to address the question of how we can efficiently extract information about just a single part of the system by the so-called density metrics, which we can then use to illuminate the physical consequences of entanglement. And as soon as we can, after we have developed these concepts, we will make them concrete in the simple setting, namely for systems made out of 2-level systems. So let us assume that we have a system made out of 2 parts, each having capital N or capital M states that we label by a corresponding index, little n or little m. These are indices of certain basis states, which we can again take to be normalized and orthogonal. And then we could, for instance, carry out a measurement that tells us which of the different states these parts are in. We can certainly obtain the probabilities for these measurements if the 2 parts are completely independent of each other, so that each of them has a separate wave function. But this is a special case where we call this system separable. In general, we need a wave function that depends on both indices, so that it can also capture correlations between these outcomes. And so we again end up with a wave function that covers all the possible combinations of these outcomes. It is then natural to write the corresponding quantum state in the following way, where we introduce a new basis that combines the basis states of the 2 parts. Here each basis state Nm just says that the first part of the quantum system is in state N and the second in state M. Now the state that we have written here is already the most general version of a state of the composite system. In particular, this already covers all superpositions of these states, so the superposition principle is already fulfilled. Note that this indeed forces us away from just considering separable states. In such a separable state, the wave function is written in terms of 2 factors, which depend on just one of the 2 indices only. However, you can check that the superposition of separable states is in general no longer separable itself. These states, the general ones, are then called entangled. And we will invest quite a lot of time in this chapter to understand what this entails in specific settings and in physical terms. Just for information, what we have constructed here is mathematically known as the tensor product of the states. This is denoted by a circle and a cross in the middle, and often enough we would even omit this symbol for this multiplication, because this is the only product that we ever encounter between 2 such states. Already by notation, it is clearly distinct from the scalar product between a dual state and a state, or the product of a state and a dual state that we use to define operators. The only important point here is to realize that with this tensor product, n and m still both make up the index of a vector, so psi n m is not a matrix. There's a very simple way to think of this, namely this is really just like interpreting n and m as containing the digits of a single number nm. Then n would contain the leading digits and m the trailing digits, and if they both say run from 0 to 9, then nm would run from 0 to 99. So in our context, this tensor product is always quite simple, because we just enumerate all the possible states of the composite system by this combined index nm. It is precisely this picture that guides us when we want to concretely write the state down as a vector. This vector has n times m components, and so we break it up into different parts, namely into n m-component vectors, each obtained when we keep the index n fixed. And then we place these subvectors consecutively below each other, giving us a single vector of n times m components. Incidentally, this observation that the number of components increases so drastically is the reason why composite quantum systems can be so complex. And this is exactly what we would exploit, for instance, for quantum computation, because in a suitable superposition we can test the properties of a lot of different states at the same time. Once we have this column vector, we can also write down the corresponding row vector with the complex conjugated coefficients, and these are then the coefficients of the dual state. For the scalar product, we say that the states Nm again form an orthogonal normalized basis, and so this will again be the same as taking the product of a complex conjugated row vector and a column vector. This covers all that we need to say about the states at this moment. Next, let us have a look at the observables of these systems. These observables are still represented by linear Hermitian operators, and we can distinguish basically three different types of them. Those acting on the first part of the system only, those acting on the second part of the system only, and those acting on both parts of the system at the same time. We focus on the operators acting on each part, because the others can generally be written in terms of products of these. In the following in particular, the main point is to just appreciate that there is a systematic construction leading to observables of a very distinct structure, while the details are not too important. So you just may wish to make sure to see that everything is well defined. We will then later see in examples how this all works out in practice. So let us have a look at an operator for an observable of the first part of the quantum system. For this, recall that when just applied to the isolated part, we can specify the operator by its action on all the basis states. Indeed, taking the scalar product of the result with another basis state just gives us one of the matrix elements, and by going through all the combinations of basis states, we obtain all matrix elements, which make up here an n by n matrix. To define the corresponding observable of the composite system, we need to translate this into an nm times nm dimensional matrix. But this is actually simpler than it might sound, because there's just one natural way to go about it. We just replicate what this operator does to the first part of each basis state, so consider how it changes the first index, but we leave the second index unchanged. What this means is that in that second index, the resulting matrix must be diagonal. This matrix then has a very distinct structure, a so-called block form as specified here. What you see here is that each matrix element of the original n by n matrix, the numbers in there, has been enlarged into an m by m matrix by just multiplying it by an identity matrix of that size. When we consider the same procedure for an observable of the second part, it is even simpler. The first index, which is unchanged, is just the index of the subvectors from before, where we constructed the composite long vector. And so we really just operate on these subvectors separately. The corresponding matrix of the composite system then has these n by n matrices of the original operator on the diagonal. We can check immediately with these forms that any observable of the first quantum system commutes with an observable of the second quantum system. And so these observations on the two parts remain simultaneous. This is what we should expect conceptually, because these observations are really tied to the different parts of the quantum system. As mentioned above, we can also have some observables that extract some collective information out of the quantum system. But as we also said, these can be conveniently broken down into products of the observables of the first and the second part. So what we have written down here is already enough to generate more complicated objects, including Hamiltonians that contain interactions. With this, we already have covered all that we can say about the dynamics of these systems on such very general grounds. In concrete settings, the dynamics of such composite systems can of course be very complicated because of the richness of the information contained in the quantum state. Similarly, when it comes to measurements, we also do not need any further adaptations because the general measurement postulate holds, even though the observables can now be more complicated. So the possible measurement outcomes are still constrained to the eigenvalues, And we can still work out the probabilities from the corresponding eigenstates. And we still have the same drastic effect of measurements on the quantum system, namely that this forces the system into that eigenstate. But what will of course be very interesting is to see how these measurements can be correlated, in particular when we deal with a quantum system that is entangled. Right, let us illustrate this all for the simplest case, namely a quantum system made out of two true-level systems, for instance, two spins. So we have a composite quantum system made out of two parts, and in each part we have just two independent states. We are going to label these with 0 and 1. In practice, this could indicate spin up and spin down, but in terms of notation, these labels are more convenient. So there are two such states for the first part and two such states for the second part, and for the composite system we have to account for all the possible combinations of these states, which makes up 4 basis states. And according to the superposition principle, the most general state would be a sum of these, where I introduce some coefficients alpha, beta, gamma, and delta. So now we can group these also into a vector, and this would just be a vector of 4 components. Note that I ordered these states in a very particular way, and we need to preserve this order when we translate states to these kind of vectors. Now, as in our general construction, this can again be broken down into two two-component vectors. And if you look at the meaning of these, the vector where we have the coefficients alpha and beta has the first part of the system fixed in the state 0, and the vector with the coefficients gamma and delta has the first part of the system fixed in the state 1. Above we mentioned that we can distinguish states that are separable or entangled. So let us look what this entails concretely for this example. A separable state can be written as a product of two individual states, as indicated here. When we multiply this out, we see that the coefficients factorize in a very specific way. Denoting these coefficients again as alpha, beta, gamma, and delta, we can use this to write a simple condition for this factorization, namely that the combination alpha delta minus beta gamma vanishes. As we mentioned before, all states that do not separate in this way we call entangled. And so we can now introduce a quantity that quantifies the degree of entanglement, the so-called concurrence, which is specified here. For a normalized state, the maximal value of the concurrence is 1. States with this maximal concurrence are called maximally entangled, and I here write 4 particular examples of these, which are the so-called Bell pairs. We notice that in these we have a very strong correlation between the states of the subsystems. The structure of the first state, for instance, implies that when we measure the two subsystems in this basis, then we always obtain the same values. And this is even though the values of the measurements themselves are completely random. Similar correlations also appear in the other states, where sometimes the values are always the same and sometimes they are always opposite. But in some way we are jumping ahead here because we have not fully established the observables for this system, which we need for the measurements. But once we are done, and that's very soon, this important picture will indeed be confirmed. Okay, so let us see then how this all works out with the observables. Well, for the individual systems, these are all related to the Pauli matrices, and so let's look at the observable sigma x as an example. As a matrix, this is of the following familiar form. And in Dirac notation, it is this operator here, which I denote as x. This takes the state 0 and converts it into the state 1 and vice versa. Now let us work out what this operator does on the state psi of the composite system when we apply this operator either to the first or to the second part. We start by applying it to the first part. So whenever we have a 0 in the first entry of the basis state, we replace it by a 1 and also the other way around. Then we reorder the result so that the basis states again appear in the original order, and from this we can read off the resulting column vector. In there we see that compared to the vector that we started out with, the first two entries are interchanged with the last two entries. But this is the same as applying the following matrix to the original vector as indicated here. I call this x1, where the subscript indicates that this is the sigma x observable for the first two-level system. This indeed still very much looks like the Pauli X matrix, but with the different entries replaced by blocks obtained from the multiplication by an identity matrix. So if you multiply an entry 1 by an identity matrix, you just get the identity matrix. And if you multiply 0 by the identity matrix, you just get a 2 by 2 block with zeros. This follows our general rules established above, but here we constructed this very explicitly by insisting on the compatibility of this operator with its action on the first part of the system. Now let's see whether this also works out when we apply this operator to the second part of the system. We can still apply the very same rules as given above, but just have a look at the second entry in the basis states. So we obtain the result stated here. And then we again bring all the basis states back into the original order in order to read off the corresponding vector. This tells us that the first two coefficients are now interchanged, and so are the last two. And this follows from the original vector by applying the matrix x2 given here, as you can check by a matrix times vector multiplication. Well, we can again interpret this as a block form, and then this is just obtained by placing the original Pauli X matrix onto the diagonal blocks of this 4x4 matrix. Analogously, we can define observables for sigma y and sigma z as given here. If you like, you can check for each part that they still fulfill the usual commutation relations, while the observables for the different parts commute. To describe what happens when we carry out measurements, we need the eigenvalues and eigenstates of these observables. But they again take a very simple form. The eigenvalues of these observables are still just plus or minus 1, but they are now twofold degenerate. The corresponding eigenstates are separable states, where we combine an eigenstate from the observable of one part in question with an arbitrary state of the other part. I give here, for example, the eigenvalues and eigenstates of z1 and z2. Note that they have the same eigenstates, as these are simultaneous observables. And when we now make a measurement of these observables, we obtain the probabilities as stated here. Now it is in these probabilities that the physical consequences of entanglement is hidden. In particular, with this we can verify what we said above about the correlated outcomes in the maximally entangled Bell pairs. And these correlations are really the key message of this segment, and so we have this firmly in the bag. In the remainder of this chapter we carry on to explore some further physical consequences of this entanglement, and in particular what this means for the properties of the two different parts and the way they influence each other. For this, we need to introduce a new object, a generalized version of a quantum state, which is called a density matrix. This has many other uses, so we first introduce this in general terms, and then we will return to this example here.